Hey guys, and welcome to Functional Print Friday, and welcome back to my shop. So in last week's video, we started the process of designing our own tachometer input for touchdro on this lathe. And we got as far as figuring out a Hall effect sensor that works with touchdro, and we just put some magnets here on the chuck and just sort of did a test to make sure it was actually picking up the signal. And it looked good on the oscilloscope, and it was working on the touchdro screen. So I think it's time to move on to actually designing and 3D printing a pickup for the spindle itself to house the magnets. So let's come around to that side of the machine. Now, where we left off in last week's video was taking a look here at where the spindle comes through this side of the headstock. And this is the part of the spindle that turns on this side. And thinking about maybe a way to have like a ring that would slip over the outside of this that has the magnets as part of it. And then the next part would be figuring out some kind of a mount for the Hall effect sensor that would maybe either go around this OD, or mount somewhere over here onto the side of the headstock so that that Hall effect sensor is held in a position where it can read the magnets as they come around on the spindle. Now, I'm a little concerned about the magnets coming off. So I think I want to try and design it that the magnets are on the inside face so that once it's slipped over the spindle, there's no way for the magnets to get out. I had entertained just pressing the magnets in with a tight press fit from the outside and maybe even gluing them in as well. There's going to be some vibration that comes through the spindle, like if we're doing a heavy interrupted cut in metal on the other end where we have a workpiece chucked into this lathe. So I want to make sure whatever we design that it's as bulletproof as we can make it to keep those magnets in there. Now, the fine line we have to walk is if the magnets are on the inside, that magnetic force is going to have to travel through the PLA and then through the air gap to be read by that Hall effect sensor. So we don't want it super thick either. So, all right, I'm going to go start drawing and see what I come up with, and I'll bring you guys back. All right, and here is the design that I came up with for this. And I settled on 8 magnets for this. It just kind of seemed like the right amount for the size of this. We probably could have squeezed 10 in there, but I think honestly anything more than 3 is probably sufficient, even at low RPMs. And I just figured, 8's plenty overkill and is definitely not a problem from a design and printing perspective. So I kept with the original plan of putting these on the inside. So this face here on the inside is where these guys are going to press in from, and then they'll be captured in place because once this is slipped over the spindle, there's no way for them to back out, and they can't get out of the other side because they are closed bores. So if we knock out the bottom of this, you can see the bottom of those bores, and it's a flat bottom bore, and this is a curved surface. So I think I had 2 millimeters of solid material from the center point, next down to maybe about 1.8. Here on the sides, but that should still be plenty of material to retain these guys, even if the spindle ends up going, I don't know, maybe up to 2,500 RPMs at some point in time in the future. And I also added some bores up here on what is going to be the side that faces out. And the reason I did that is because if both of the sides just looked like this, once this is in place on the spindle, we'd have no idea where those magnets are. I mean, I guess we rotate it around and see that they trigger the Hall effect sensor and no one is there, but there'd be really no way to troubleshoot, getting the magnet in the correct position if for some reason it was not triggering the Hall effect sensor reliably. So I thought let's go ahead and just put some, some small bores on the face that is going to point towards us when it's installed so that we can just, see the exact position of those even though we can't physically see the magnets anymore. And I'll open this up in Bamboo Studio and just color the bottom of each one of these bores white, and then let it do a couple layers of white filament to make those dots. But if you don't have a multicolor printer, you could just print this out and just go around with a paint marker and just dab in each one of those holes, and you get pretty much the same effect. So, all right, I'm going to go ahead and print this out, and let's see how we did. All right, and here is our finished print, and it looks pretty good. I did a brim just around the inside because as we beveled both sides of this, there's not a whole lot of contact area, and there's quite a few interruptions here in the print with some overhangs at the top where those magnets are going to press in. And it stayed on the bed just fine. You can see the recessed areas where I colored those in white. That's actual white filament in there. And that came up pretty good. The whole idea there is once the magnets are in there and we slip this over the spindle, we can't tell where the magnets are. So just from a debug perspective, I thought it would be useful to have a corresponding dot on the outside of the ring there. So, all right, we got to figure out how to get magnets pressed into this. I oversized these holes by 0.1 millimeters, figuring that with the overhang here, the way that this was going to print, they'd close up a little bit. We might have to go a little bit bigger, but I'm hoping that we can get the magnets pressed in on this one. So, all right, let me get set up with the tools that we're going to need to do that, and I'll bring you back. Okay, I've been circling the shop for about 5 minutes trying to figure out the best way to do it. I think if we use some of these Knipex smooth jaw pliers and we stack maybe 2 magnets on one jaw and slip it like over like this, we can press it into place. Let's see. The other thing we have to be really careful about is getting all of the magnets with the same polarity. Now, in the past, I've done that just by keeping them in a stack like this and putting the stack on the arbor press and just pressing one at a time and then moving to the next part. Because this is a ring, we can't use the arbor press. So I'm going to have to be really careful here to make sure that I'm always, I guess if we keep one on the plier and I just keep adding a magnet on top of that one, we should be able to maintain the same polarity as we go around. Because there's no way I'm going to get the magnets out of that. Once they're pressed into this, that's it. If I screw one up, we're reprinting this. So, all right, let's try it. I'm going to try 3 on the pliers. You know what? Now that I think about it, I think these only worked in one direction from a polarity perspective for the Hall effect sensor too. I guess I gotta go check it there first to make sure that we have these facing the right way. Let's see, so yeah, the face that's sticking out would be the face that needs to trigger the Hall effect sensor. All right, I guess we had a 50-50 chance. We won the lottery on that one. So they're facing the right way right now. Let me flip it over and just make sure that I'm right. So it shouldn't work this way. Yeah, and sure enough, it does not trigger it facing that way. So we have to have the magnets facing that way. Okay. If you want to make your own parts for this build, the STL for this, as well as everything else we're designing as part of this video and every video on this channel, is available completely free on my site, fpfdesigns.com. I'll link that down in the description below. And this, by the way, is working out really well for pressing these in. If you don't have a pair of these Knipex pliers, they're pricey, I'll admit. I tried another brand first. I think like the Crescent ones, yeah, nowhere near as good. The Knipex is the way to go. I'll link these down in the description as well. Okay, that is all 8 in place. I'm just going to run my finger around and make sure they all feel like they are seated to the same depth. And looks like they are, because this is not going to work unless all 8 of these trigger the Hall effect sensor. All right, let's go back over to the sensor and just see if it's triggering it through this. Okay, it does. We have to get pretty close, unless I'm not lined up on the magnet. It's not too bad. I mean, there's not a whole lot of gap there before it triggers. Maybe, actually, there's probably about 3 to 4 millimeters of air gap there. Make sure that they all actually do trigger it. The other thing I'm realizing that I hadn't really thought through until right now is the spindle itself is steel. So when we put this on the spindle, it's possible that some of that magnetic force dissipates into the spindle itself. So, I think we're just going to have to press this on and see if it works. Okay, looks like it's triggering. I could definitely get closer. I'm trying to keep it at, you know, pretty much the farthest distance and just see if it's consistent. We've got probably 3 to 4 millimeters, about the same as I was seeing on the other side, gap there. So far it does not look like the spindle, that steel spindle on the other side of those magnets is affecting our magnetic flux. All right, let's turn it on and see. And yes, I'm using our 3D printed bypass key to bypass the security switch here since we have the cover off. Okay, touchdro is telling us we're doing 71 RPMs. That's way too high, but you know what? I just realized we have this set for 6 magnets. We have 8 magnets in that ring, so got to set this for 8. Okay, let's try it again. Okay, I think we're seeing 53 RPM on there, and I am in the gear that is 50 RPM. So I think that's right based on the test that we did before, but let me double check it with the optical RPM meter. Okay, we were seeing 53, 54 on this guy. The reality is our magnetic pickup for touchdro is probably more accurate than this guy because there's only one reflective pickup point on here, and that's a pretty low RPM. So let's try something higher. Okay, that was in M4. Which shows 180 here on our chart. We already know that all of our numbers are going to be a bit higher than this. Let's jump right up to M1, which should be 510 RPMs. Okay, that should be 980, which I'm almost guaranteed we're going to be over 1,000. In fact, yeah, I know we're going to be over 1,000. All right, this is working great. Let's just go for broke. I'm going to go into H1, 2,000 RPMs on the chart, probably more like 2250 in reality. Hopefully nothing gets sucked into the gears here because everything is going to be moving quite fast over here. Again, the only reason this is even running is because we have this bypass key in. Normally the lathe wouldn't even operate with the, without the safety cover off over here. So yeah, crossing my fingers. Good news, nothing flew apart. Bad news, I was only seeing like 1,300 RPMs up there on touchdro, which is wrong. Actually, I'm going to turn it back on and see if I can verify that on the chuck. I think it's not reading the magnets. We could try getting closer. Maybe I'll get the scope hooked back up. Let me read this first and see what we're actually reading on the chuck. All right, so as you can see there, we are doing well over 2,000 RPMs, and we were not picking that up on touchdro. So let me get the oscilloscope hooked back up. Let's see if we can figure out what's going on. Okay, good news. When I plugged the oscilloscope in, I realized that our sensor had actually just moved a little bit. It was a little bit further away from the ring. It had moved like in towards the headstock. I don't know if it was the vibration, moved the base a little bit maybe. This is not like a super flat surface here. Maybe the magnetic base just turned a little bit. But I put it back to where we originally had it, and the signal looked good on the scope, and we had the right speed on touchdro. So I think we're in good shape. I'm going to play around a little bit more here just on the oscilloscope. I'll do the math with the frequency that we're counting here just to make sure that that agrees with touchdro, but the signal looked really clean. I think we're still good with 8 magnets on there and the top speed on this lathe. Okay, we were seeing 292 hertz roughly. It was flipping around a little bit because the motor RPM is going to vary a bit on the lathe, but we're seeing around 292 hertz. So if we take 292 times 60 divided by 8, because we had 8 magnets, we get 2190, which I have to check the footage, but I think we were seeing like 2198 or 2195, somewhere right around there on touchdro. So yeah, I think we're good. In the interest of testing everything that we possibly can before we move on to the next design step, I think I'm going to push this ring further over on the spindle. And I'm also noticing that running at that RPM, the spindle actually gets slightly warm. It's not hot, but it's warm. It's probably, I don't know, maybe 115 degrees Fahrenheit. Somewhere around there. The lathe also wasn't running that long. And I don't often run the lathe that fast. But it does have me a little bit worried about trying to mount to the outside diameter of this, because this is also warm. This cap here is essentially what holds the bearing in place on this side of the spindle. So the bearing and the spindle are both warming up a little bit. I think this ring will be fine. It's a nice tight fit on there. I'll be surprised if this stretches enough to spin on the spindle. But I am a little bit worried about trying to mate to the OD of this bearing cap for the other piece. I think we're going to have to figure out something else, because that I fear would probably slip, especially since this is cast, which means there's a little bit of a draft angle on this. I hadn't thought about that before. So yeah, we probably cannot mount to, well, to the OD of this. We're going to have to figure out some other way to mount our piece that holds the sensor. All right, let's get this pressed on. All right, that's working great. We are now, though, at what is probably going to be the hardest part of this build, because we've got to design something that is going to reliably hold that sensor at a consistent gap from those magnets while this guy is in operation. We don't have a ton to work with in here, and we have a bunch of clearances to consider as well. We can't really be much further out than where this ring is. Maybe the width of my pinky tops, because that safety cover comes across here and the spindle actually sticks out a bit. So that cover probably comes over to somewhere in this region. So we really need to keep the profile pretty low. We do have a threaded hole here. I think what this is one of the shafts that the gears run on inside the headstock. I think it's threaded so that it can be removed. That's my guess, because it can't come out with the bearing cap here. But if we took this off and we threaded something into there, I bet you we could yank that shaft out with like a slide hammer. So we could probably use that to mount if we're gentle. I think if we tighten down real hard, we risk spinning this shaft. Unless it's keyed in place on the other side. It might be, I don't know. I don't want to find out. Last thing I want to do is be opening up this lathe to repair it. But my guess is we could probably gently thread into that. And then maybe we use the face of this and this to keep it from turning. Because if we mount there, obviously we don't want it to rotate, but it can't rotate if we follow these faces of the bearing cap. Now the trick there is, we know this has a draft angle on it. This probably has a light draft angle on it as well. My guess is this face is probably flat. And it's going to be tricky to measure the distance of the position of this relative to everything else. I guess we really only need to know the distance of the center of this away from this, since it doesn't really matter exactly where on axis we are. It's still going to be tricky though. If only there was a way to cheat. Yeah, where has this been all my life? This is what I'm talking about. Okay, so the scanner's struggling on this reflective surface here, this shiny metal. I'm going to get some painter's tape. cover this up so we can get that surface as well. So this 3D scanner is the CR Scan Otter from Creality, and Creality reached out and asked if there was any projects I was working on that I might benefit from having a 3D scanner for, and if so, they'd love to send one out completely free of charge to basically sponsor the project. And they caught me at the right time because I was really dreading drawing all of the geometry for the spindle bearing cap, the spindle itself, and just the relational positions of all those parts to each other. Yeah, it could certainly be done, but it wouldn't be fun to do with all those complex draft angles because these are all cast parts. And this thing just absolutely makes it easy mode scanning all of this geometry. So this scanner does up to 20 micron resolution, and it'll do it at up to 20 frames per second. Now, you're gonna get the 20 micron resolution regardless of what you use to scan with, but if you wanna get the 20 frames per second, which is pretty fast for 3D scanning, you're gonna need a fast enough machine to do that. This is not a standalone device. It plugs into the USB port here on my laptop. And my laptop has a Core i7, and I'm pretty sure I'm getting the full 20 frames per second here. It seems very responsive to me. Now, the scanner uses infrared light to pick up the actual 3D geometry, but if you look down to the bottom left, you see that there is a color view as well. There's a separate CCD on there that will actually pick up all the colors while it's scanning, and it will map those colors onto the model when it's completed, which I, kind of thought they're just trying to add some sort of feature to stand out from the crowd that isn't really practical and or wouldn't really work that well. But yeah, it's pretty cool. Stick around to the end of the video. I'll show you what this thing is actually capable of doing. Okay, it looks like we've got a pretty good scan here. There is a bunch of weird issues in areas where, like I was trying to sneak in underneath here where these gears are blocking and from different angles, so we didn't quite get those. And the end of the spindle is reflective, so we have some artifacts there. But I think we have good geometry around everything that we need, which is really the location of this bore and the shape of our spindle cover here. So let's try and process this. All right, so the first thing I'm going to do is get rid of everything we don't need. So let's just delete everything in this scan that is not pertinent to our design. All right, that looks like everything that we still need. So let's go ahead and process this and see what we end up with. And once that finished processing, I went ahead and exported that as an STL and then imported that into CAD. And I could model directly on top of this, but just given the fact that there's some missing sections here because I couldn't angle the camera to capture that data without actually disassembling the lathe, I figured it's probably easy to just go ahead and trace solid objects on top of the 3D scan and then work from those solid objects. So if I hide this, you can see that is what I have done here. I just basically transferred all those into solid objects. Now, I still don't know that any of this is actually the right size. I'm basically trusting that the 3D scan was accurate dimensionally. So the next step is going to be to go ahead and actually model like a test piece on here. So here's that bore that I want to work from. And I figured let's just model a test piece on the top of this and then just see if everything lines up. So let me do that and I'll bring you guys back. Okay, and here's what I came up with just to, again, give us sort of a quick test to see if our dimensions are actually accurate. So we want to confirm that it's going to key correctly against these curved surfaces, that the height of these steps is correct, and that we are roughly centered on this bore. So I'm going to go ahead and print this piece out because I don't want to, it's tempting to start trying to design a way to mount the sensor board on here and actually use this, but it's just wasted time until we confirm that these dimensions are actually accurate. That's the first time I've used this 3D scanner, so let's print this test piece out and see what we get. All right, our test piece is done. Let's see how it actually fits. So it looks like we have contact on all the faces. We're sitting up against this face here, this face here. That last one, I might be able to slip like a sheet of paper. No, actually, I think that one's touching too. I think it's just deceiving because we have this rounded over edge there that I did not duplicate in the test piece. How's our bore look? Yeah, bore looks, if not dead center, it is really close to center. I'm getting hung up on, I think this fastener head, yeah, that fastener head's a little bit proud of the casting. Yeah, so is that one. I didn't catch that in the scan. I thought that one was flush, so might have to add a little bit of clearance. That's what I'm kind of catching on as I was trying to slide this guy down in a position. But yeah, everything looks really good. Let's try a bolt in there. All right, that bolted up on there, no problem. We are dead center on that bore, or as best as I can see, dead center on that bore. So we can tighten up the clearance hole in our final design for this bolt to slip through as well. Now, again, this is just a test piece, but there's a lot that we can learn from this. And in fact, just by dumb luck, I think the front face here of this test piece is right about where I want the actual sensor to sit in relationship to the OD of called our tone ring or our magnet ring here on the spindle. So we probably don't want the front face of the actual final design to be that far forward, but we do want the sensor part on that board to be about that distance away from the ring. So that's good. We can use that measurement from our test piece to try and treat that as the final landing position of the sensor part of the board. So I think that's the next step. I think we've got to go back up to CAD and work from the dimensions of our test piece and come up with a design that's actually going to hold that board, and then also think through how we're going to protect this as well. If you notice, my hands are getting black every time I touch anything in here because there's dust that comes off of these belts. It mixes with the grease and oil here underneath the side cover of the lathe, and that stuff is just going to build up more and more over time. This machine, I've only had this since I think September of last year, so this is probably the cleanest it's ever going to be. And there might be some chips that accumulate in here eventually as well. So that's a long way of saying I don't want the board just directly exposed to everything going on in here because it's eventually going to get gunked up with junk and probably stop working. So I need to think about how we're going to enclose everything as well. So, all right, let me go start drawing and I will bring you guys back. Hey guys, I'm sitting here editing this week's video and I'm up to the point in the footage that you guys just saw, and this video is already going to be over 30 minutes long. So I want to break this up. Let's tackle the final design for the sensor mount, the wiring, all the fine tuning, buttoning everything back up and testing it next week. I went through a lot of different iterations in the final design, and in fact I even made an 11th hour change this morning adding in clear filament for a part of it. I don't want to rush through that. So let's tackle that next week. But for this week, before I wrap up, I want to go down and try out some full color scanning with that Creality Otter scanner. So let's go do that. All right, I mentioned earlier in the video that this guy will do full color 3D scanning, and it is really pretty impressive. So I went and I grabbed some just random objects from around my shop to demo this for you guys. So it's my impact driver out of my everyday toolkit, an old pair of pliers, and this is actually a piece that Creality shipped along with the 3D scanner just so that you're able to confirm your calibration on the device. I've got them set up here on a turntable. We're not going to scan these all at once. We'll scan them one at a time. I'll probably speed up the footage because while it doesn't take that long to do the actual scanning, it does take a while to process the scans once you've completed them. So I'll set the laptop off over to the side so you can see what I'm doing. I'll make sure I'm running the screen capture on the laptop, and let's see what we can do. Okay, here's the scan data from the pliers, and I think I only rotated these around maybe twice, and I didn't change my position a bunch, so we don't have good data all the way underneath stuff. I would have had to flip these guys over. And by the way, you can do that. You can pause the scanning, reposition the object to see part of it that maybe you can't see just based on how it's sitting, and then continue the scan. But that looks pretty good. Let's move on to the impact driver. All right, this one took quite a while to process, but wow, does this look good. Now, I only scanned just the top of this, so we again are gonna have missing geometry here, like we don't have the bottom of it because I didn't flip it over and scan the other sides, but just what it could see spinning it around the turntable, like that is amazing. Now, one thing to point out, just like we had the challenge with the spindle on the lathe, the chuck here, that the hex bit goes into is a really shiny, smooth material, and it just didn't pick that up. So if you have stuff like that that you want to scan that is a really reflective surface, you're going to have to put something on it. They make sprays that you can use, or in the case of the spindle on the lathe, I was able to just put a piece of tape over it and get it no problem. But I mean, look at the detail there. Like it's not perfect. I also only spent, I don't know, maybe a minute and a half tops scanning this. I think if we tried a couple different positions, we'd probably get even more detail out of this, but just wow. All right, let's try that little baby owl. Okay, and here's the scan data from the last one. This is that little hatching baby owl, and it looks amazing, and it looks pretty complete as well. Now, I can nitpick and call out some things that just don't make sense, like it kind of looks like there's like some watercolor paint here spilled on the shell. That's like violet and blue and purple, pink, a little bit of green. If we look at the original model, I mean, that's not there. So I don't know if that's like reflected light or what happened, but I mean, we're nitpicking. Overall, this looks amazing, and because this had a flat bottom and there's really no details that are obscured by this sitting on that bottom, this looks pretty manifold as well. Let's turn the color off. Yeah, look at the mesh on that. I mean, that looks really good. I don't know, what is that there? Is that on the model? Yeah, that is on the model. I didn't even notice. There is like a little protrusion from the model there, and that picked it up. So I'm definitely excited to have this in the toolbox for future projects. There's a lot of things that I just don't tackle because trying to draw the geometry to either model from or to fit up against is just going to be too much work. And honestly, I really wish I had this when we did the design for the trunk and fuel door release for the Corolla. That thing was a nightmare to measure and model. Kind of similar reasons to why the lathe would have been a challenge with the spindle, because that was an injection molded part. So nothing was straight on it. Everything had some sort of an angle, and you might not think that's a huge deal, but then when you go to measure where faces intersect and they're not flat, it is just a time suck to try and figure out where those faces actually are when they're not parallel to any other faces on the model. Guys, as always, thanks for taking the time to hang out with me in the shop for this week's video. I'm really excited to share the rest of the design work on this with you. All of that is done, and in fact, I'm waiting on some of the final pieces to print right now, but here is a slightly earlier version of the final design that we're going to take a look at next week, and there's a cover that goes on top of this as well. So next week I'll cover the design for that. I'll show you the other pieces as well, and we'll get this guy installed, wired, and finished up. If you enjoyed this video at all, if you got anything out of it, do me a favor, take a second, hit that like button. It really helps out the channel. Also gives YouTube a better idea of the type of content that you actually want to see. And if this is by chance your first time here on the channel, we do all functional prints. There's a new one every single Friday. So check out some of my other videos. And if you like what you see, hit the subscribe button. And if you do, I'll see you next Friday.